Welcome back, everybody. I hope your discussion yesterday about model diversity and goals went well, and that you're all ready for another fun day of modeling and talking about projects. So yesterday, day one showed us what models are good for, and that we need many different models at different levels of description. We saw that there are many goals for different types of models and different types of models with different strengths and different weaknesses. So the question then becomes, of course, how do we choose which model to use? Every textbook teaches a different toolkit, and every scientist has their own favorite approach. But what fewer courses and approaches teach you is the meta-science component, which is the process of picking your model goals and approaches to tackle those goals. So how do we do that? I'm going to start today by going through some options here that are obviously wrong, but please bear with me. The first option is I could pick a type of model or toolkit and try to apply it basically wherever I can, wherever possible. Of course, this means I get really, really good at this particular type of modeling, but it also really seriously limits the types of questions that you can ask or that I could ask. For example, let's pretend that I absolutely adore optimal control theory. It's totally the best. But if all I do ever is optimal control theory over and over and over again, I might end up painting myself into a corner. I'm a one-trick pony. I'll limit my impact and the progress I can make in science. Of course, I could also go with my advisor's favorite toolkit. But this, of course, has exactly the same problem. What if the problem I'm studying really just isn't compatible with optimal control theory? I want to take spike trains and study them with information theory instead. I'll have a hard time fitting that square peg into this round hole if I really stick only with optimal control theory. You might think it's also good to use a fashionable toolkit, something that's really in right now, really hot, really state-of-the-art, so you can publish in high-profile journals. You might say, hey, you know what's really in right now? Deep convolutional neural nets, AI. I am going to apply state-of-the-art deep convolutional neural nets to this problem, and therefore I'll get insight. But the issue is that randomly applying machine learning, or any model that's fashionable for that matter, it's not actually going to get you very far. A model just fitting the data just by itself doesn't provide a ton of answers. And of course, on the other side, you could just go with your gut. Which model you think might be the right one. The problem is, of course, that our intuitions need to be nurtured. That's really what we're starting to do in the Neuromatch Academy program, is begin to shape that intuition for all of you. So basically what we need to do, and what we're going to start to do over the next 3 weeks, is learn how to ask really good questions to build good models in order to be able to answer those really interesting scientific questions themselves. So remember this process diagram from yesterday? We're going to get our hands a little dirtier today to see what each of these steps might look like in a real model building exercise. Today in your tutorials, you're going to start doing a little bit more of that practicing to start to lay the groundwork for building your own models in the future. So the first thing that we need to start with, the first thing we need to think about is how to ask the question and how to ask a really good question. If you don't ask a good question, you're really going to get in trouble. Good questions are about what, how, and why systems behave the way they do. And bad questions, in contrast, have kind of yes or no answers, or they don't provide any of these insights. So let's have a look at some examples. It's really important to be as precise as possible in figuring out your questions. Imprecise questions are going to lead to rapid failure. So here's some examples of some not so great questions and their better question counterparts. And let's go through each of these in turn. One not so great question would be, how does a clock work? This is a really imprecise question. I have all sorts of follow-up questions if this is the question that you bring to me. What level of analysis do you want to look at? Do you care about gears or hands or time as an abstract concept, electricity versus mechanical movement as a driver? A better question is, how do the angles of the hands of a clock predict the time of day? This gets us a much more narrow, precise question that we can then go try to answer with specific observations or experiments. The second one is also a not so great question. Can we predict whether a rat will turn left or right from neural activity? This is really not so great because it doesn't specify which neural activity you think is important to look at, or which time windows around the behavior you're going to look at. Do you care about predicting before the rat turns or after he turns? Do you care about the rat's decision to turn or his motor preparation and execution? This is also kind of a yes or no type of question, but it doesn't say what counts as prediction. Do we care whether one neuron's spiking is less when the rat turns left versus right? Or is it the population activity that we're interested in? Is 52% prediction accuracy sufficient, or maybe 54%? So a better question to ask is, which types of neural activity, when, and which types of analyses significantly predict whether the rat will turn left or right? Maybe you can predict after the rat turns, but not before. Or maybe not before 100 milliseconds before he turns. Maybe it's population activity and not single unit responses that are the key. Maybe you can predict from some areas, but not other areas of the brain. And maybe only linear models work, but a neural network doesn't because it overfits. So once again, precision in our questions is really the name of the game. And finally, here's another not so great question. How does the motor system work? Again, this is really just not precise enough. Do we care about peripheral or central nervous system? Do we care about muscles or motor commands? Which areas of the brain do you want to look at and why? So all of these follow-up questions show that this question is really very imprecise. And a better version would therefore be to ask specifically how sensory noise, like noisiness in the environment or noise in the sensory input, how that sensory noise might change the behavior of the system. Does this noise introduce systematic motor biases? Does it reduce performance accuracy or reaction time? This can tell you about how the motor system works actually, but in a much more controlled and precise way. So the key really is to try to ask as precise questions as you possibly can when you're learning to model. It's a skill we all have to work on all the time to be able to ask these really careful questions, but I promise you it's well worth the effort. So in these next videos today, we're going to go over this meta modeling process with you. We're going to walk you through a lot of the potential pitfalls that you might run into, so you can avoid these dead ends in your own projects, and you can learn to build precise and powerful models yourselves. So I want to preface these next few videos also by saying that we're going to be doing this with just one model from one tiny corner of computational neuroscience. Some of the details of this model, some of the concepts, some of the background knowledge, and so on, they might be unfamiliar to you, and that's totally okay. Just try to pay attention to the modeling process from question all the way through completion. And so most importantly, try to have fun today.